Hello, everybody, and welcome to today's combustion webinar. I'm Peng Zhao from the University of Tennessee. And today, it's my great pleasure and honor to introduce you our speaker, Professor Audrey Van Duyn. So Professor Audrey Van Duyn is Distinguished Professor in the Department of Mechanical Engineering at Penn State University. Meanwhile, he holds professorship in the departments of Chemical Engineering, Chemistry, Engineering Science and Mechanics, and Material Science and Engineering. He also serves as a director of the Materials Computation Center. Professor Van Duyn obtained his PhD degree in chemistry from Delft University of Technology in 1993. He is the inventor and main developer of the reactive force field method and has published over 525 journal articles, and over 450 are related with the reactive force field. And he has distributed the reactive force field code to over 2,500 university and industrial research groups all around the world. He is awarded the Marie Curie and Royal Society Fellowship in Newcastle, and the K.K. Cole Early Career Professorship, and a Penn State Faculty Scholar Medal. And let's welcome Professor Audrey Van Duyn, and thank you very much for your time and lecture. The podium is yours.
Thank you, Peng. Thank you very much for your kind introduction and for giving me the opportunity to present my work here. Now, so I'm going to show essentially a couple of highlights of my combustion work. Most of it is a couple of years old because of reasons we have kind of moved more from combustion into material synthesis, but I hope that whatever I present will still be of interest for this community. So just for a quick outline, so I'll give some background regarding behind the ReaxFF reactive force field method. And show how we actually got to where we currently are in the ReaxFF combustion force description. So that starts essentially with the initial force field we developed in 2008, and I'll show some of its applications. Talk you way through some upgrades that we made in 2016. That includes kind of somewhat daring applications to things like ignition front speeds and these type of things. So, and then we in 2016 we developed a second generation force field. I'll show you some of the recent developments and kind of new directions that force field allows us to go in recent years. And then I said my group has really sort of crossed over from combustion into material synthesis, and fortunately there's many good connection points between combustion chemistry and material synthesis, and I just want to highlight some of those. All right, so why do we do this? So simply because combustion reactions are relatively complicated, even for arguably the simplest of hydrocarbons, methane. We have a pretty significant chemical space that we have to cover. While the basic reactions look relatively straightforward, there's all sort of side reactions depending on pressure, temperature situations you're into that one has to consider. And so if you really indeed are worrying to go all the way to soot-type particles, there's typically thousands of different species that may may be relevant, even for the simplest of hydrocarbons. Even for if you simplify it even further and we go just back to hydrogen, then we still have 7 species and 19 reactions. So that's not completely trivial, that's a bit more manageable. But the complexity speeds up very, very dramatically. And so if you go to larger hydrocarbons, clearly this picture only gets more complicated. And so as such, we felt that there's a need for a simulation tool that can essentially run reasonably reliable reaction kinetics for relatively large systems. And that's pretty much what the ReaxFF reactive force field method provides. This is a method that allows to do regular molecular dynamics simulation. So that means 10,000 to 1 million atoms or beyond if absolutely necessary. It can be trained to be quite accurate for reaction barriers, and it can cover a wide range of species, and it is predictive. So it's not something the user doesn't have to say this reaction happens at that iteration. It can essentially predict these things rather than reactions being direct input for the user. So if you look at, so if you want to simulate chemical reactions, there's essentially a bit of a hierarchy of computational chemical method that comes into play there. And so my group is more or less sitting at the border between quantum mechanics methods and traditional force field method. So quantum mechanics clearly can do chemistry. You can break bonds, make bonds in quantum chemistry, but quantum chemistry is computationally very expensive. There's clearly improvement in that field. The area that quantum mechanics can be applied to is getting bigger as time goes, but still practically 1,000 atoms is a pretty big system for quantum mechanics. And if you want to do dynamics, a picosecond to a nanosecond, a picosecond is pretty much kind of your time frame. Force fields traditionally are much, much faster. A couple of million times faster typically. Traditional force fields wouldn't allow us to break and make bonds, but reactive force fields, of which reactive F is one of them, allow us to essentially break and make bonds. They're typically a bit more computationally expensive than traditional non-reactive force fields, maybe a factor of 50 to 100, but it still allows us to significantly scale up for quantum mechanics. So this is kind of a reactive F-sits. It's a little bit slower than traditional non-reactive force fields, but it is substantially faster than quantum mechanics. Okay, so how does reactive F work? Just a couple of highlights of that. I don't want to go too deep into the equations. But what it essentially does is it uses a bond order concept. Bond orders we are kind of somewhat familiar with from our chemistry courses. So we know about single, double, and triple bonds. So that's bond order 1, 2, and 3. Now we assume in these bond order-based force field that there's actually a continuous relationship between bond order and bond distance. So the bond orders can also have values of 2.5, 0.25, anything between essentially 0 and for the carbon systems 3. And this was a concept that was introduced by Don Brenner and Tursoff in the late 1980s, early 90s. And these force fields are still quite popular. Reactive F essentially distinguishes itself from these sort of first generation bond order potentials in that the bond order range is much, much longer. So even at 2 angstrom, this is for the carbon case, even at 2 angstrom, reactive F still only partially breaks that carbon-carbon bond. There's still half of a bond order left. And that allows reactive F to essentially predict transition states with reasonably good accuracy. Also, reactive F has a full suite of non-bonded interactions, so van der Waals and Coulomb interactions, and that clearly allows us to also transition from systems that are completely dominated by chemical bond breaking to systems that are actually dominated by weak interactions. The Coulomb interaction, we calculate charges, so the reactive has the polarizable charge function. So every iteration we update the charges. That means that we also can transition from covalent materials to ionic materials. So reactive F is not more accurate than DFT. We can, if we train it well, we can approach the DFT accuracy. The DFT is arguably much more transferable than reactive F. But the main thing is that reactive F is significantly faster. Even for small systems like 400 atoms, we get a factor million. And the bigger the system gets, typically the better this comparison becomes. Because reactive F scales roughly linear with size, while DFT scales with n to the power 3. So if you double the system, DFT gets 8 times slower. Reactive F gets only 2 times slower. So this is really where reactive F distinguishes itself from the non-reactive force fields. It is very good at predicting transition state energy. Here on top is a very important reaction for us as humans, because this is pretty much the type of reaction that enzymes use to make and break peptides, or to do other types, essentially to make and break bonds. They tease Walla molecules in sort of the right configuration. And if that happens, then Walla molecules can actually do a remarkable amount of chemistry for such a stable molecule. Remember, the OH bond is worth about 125 kcal, so 400 kilojoule or 5 eV, whatever your preferential energy unit is. But you see here, I can break 4 of these bonds with a barrier of only 20 kcal. So that's just a tiny fraction of actually the total bond strength that is involved in there. And the reason why that is, while I break the bond, I automatically make the new bond. So these are concerted reactions where essentially a bond order is essentially conserved. So this also is important in combustion reactions, especially lower temperature combustion. Here's an example of a so-called Grob fragmentation. This is a barrier. This is once again a concerted reaction. The barrier is only about 65 kcal. Reactive F reproduced that pretty well. This was actually without training. It gave a barrier about 69 kcal. This is essentially a lower barrier than any of the chemical bonds in this species. And the reason for that, once again, the barrier is so low, is because this is a concerted reaction. While I break bonds, I make new bonds at the same time. So this is very important. Any low temperature combustion reactions will be dominated by those because of the nice low barrier. But also these reactions have relatively complex transition states. So the pre-exponential factor is going to be also pretty low. So this is kind of where we start and show some particular highlights along the way of my group's involvement with combustion. So while I was at Caltech in Bill Goddard's group, I worked on the development of a so-called, on the first generation combustion force field. That the first author was Kimberly Chenoweth, hence it's called the Chenoweth 2008 force field. And so I'll show you some highlights of our JP10 application in a second. And that's been working out pretty well. We essentially developed it. We tested it out for a bunch of applications. It transferred pretty well. We also added new functionality to it, for example, nitrogen and borane. And so we essentially expanded the range of the force field. And overall, it held up pretty well. But as you'll see later in my talk, there were some issues that came up later down the line with some reaction chemistry, and particularly also with the quality of its description for graphitic materials. So this has been also captured in somewhat recent reviews. If you want to see more about how this this force field operated. Just to show you how we kind of developed this. This is not the full training set, but give you some idea how we train this. So we train this typically mostly against quantum mechanics data, typically DFT, although quite often we also drag in some experimental data, especially things like heats of formation, which are they're typically more accurate for my experimental source than for my DFT source. So here at the bottom is some of our typical data that we get in there. This is, for example, a non-reactive dihedral, so we rotate around the CO bonds. This is something that with DFT we can pretty quickly get these type of curves, so you can train the force field against it. Do similar things with angles. And then on top of that, we put some reactivity. So here's an interesting reaction. This is essentially a sort of a Diels-Alder style reaction where oxygen reacts with butadiene to essentially make this species. This reaction is exothermic for butadiene here in red. So it's, my reactant here on the left is about 20 kcal more stable than, the product is 20 kcal more stable than the reactant. For benzene, this reaction is endothermic, simply because clearly benzene is a much more stable hydrocarbon chemically than butadiene. And we see on the right that reactive F reproduces that pretty well. Now, there's a couple of things that need to be mentioned here. See that overall barrier matches quite well. In DFT, this reaction changes spin state because oxygen is a triplet. Reactive F doesn't know anything about spin state, so we just essentially train it against the lowest of the spin surfaces. And we assume then, which is clearly a bit of an assumption, that during the reaction, the spin can somehow flip by itself. This is not always a correct assumption, especially at low density systems. But since reactive F doesn't have a spin state, we only can train against essentially the lower spin manifold. Yeah, so let me show you then one of the early applications of this force field and maybe one of the early successes of this concept. We've developed this force field and we essentially try to apply it to a highly strained hydrocarbon, JP10, which is a very popular high density fuel. So it has a lot of energy stored in it because all this, high strain, when you burn it, it goes back to carbon dioxide and water and you can all that strain kind of for free. The problem is clearly that the chemical mechanism of this is not going to be trivial. There's going to be it's very hard to say just from the looking at the structure, what are the first bonds that are going to break. So we wanted to see if we could use our combustion force fields to essentially do the pyrolysis and the subsequent oxidation of JP10. And so what we do here, typically we first study the pyrolysis, and we start with pyrolysis because we had some pretty good experimental data to compare with there. And so what we do is we essentially build these type of boxes. This was in 2008. So we could run about 2,000-3,000 atom systems at that stage. Now we can run much bigger systems, but we essentially heated up at relatively high temperatures. We had to do high temperatures because we only run a nanosecond of dynamics. And you can see if you look carefully, you see indeed that the JP10 molecules fall apart and also the fragments. We see ethylene in there, we see also the smaller hydrocarbons. And then based on that, we can clearly develop reaction kinetics. We can simply, for example, just monitor the rate of JP10 disappearance. And since we do this at a bunch of temperatures, we can then try to get a sort of a temperature versus reactivity relationship. And hopefully we can extrapolate that towards an experimental data. So each of these simulations was done 10 times. because this is molecular dynamics. So to make sure that your simulation makes sense, it's good to do these averages. And we found indeed that we could get some, we can get a nice error bar out of these things. And what we got out of that, once again, this is 2008, but these here in gray are the ReXFF data points, all around 2000 Kelvin. And these are the experimental data points. So this is from pyrolysis simulation at roughly 1000 Kelvin. And we see that in this case, we actually have a very, very nice agreement between ReXFF and experiments. From this, we can get, assuming first order reactivity, we can get estimate activation energies and pre-exponential factors. And they were very much in line. Now, this is clearly not actually the level of quality, accuracy that we typically even can expect from ReXFF. We are only a half a kcal off. But especially given that JP10 wasn't actually in our initial training set, but it shows at least the concept that the concept translates quite well to molecules that ReXFF was not explicitly trained for. At the next step, we wanted to actually look at oxidation. And so we had no idea how JP10 was going to oxidize. And just to give us at least some guesses, we did the following simulation. We take 5 JP10 molecules, and we simply put them with some oxygen radicals, and we temporarily switch off the oxygen-oxygen bonds, because we don't want O2 to get formed, just to give us some sort of idea of what might happen. This is a really fast simulation. Even in 2008, this would only take us probably about 5 to 10 minutes or so. But you can see from this, we get a really rich source of data, because we can get we see that indeed all sort of oxidation happens. We see water boiling off. You see that the JP10 opens up and all that. And what we can now do is we can harvest these structures from the simulation and check out what DFT thinks of them. And so this is pretty much what it. We didn't do any retraining at this stage because we were pretty happy with the level of agreement. But these are pretty much various images that we drew from that simulation I just showed. We throw them into DFT. These are not very big. These are, what is it? About 15, 16 heavy atoms and a lot of hydrogens. And we find out that the overall trend was actually pretty good. There are some deviations here. So ideally, if you want to make it more perfect, you can essentially put this new DFT data in the training set to do some retraining. But we were pretty happy with the overall level of agreement. But this concept of using ReXFF as a source of data that you can then cross-check against DFT is a pretty nice concept, because clearly this simulation that I showed here is blazingly fast. So you can very quickly build up a series of reasonably good configurations. All right, so let me show you a fairly daring application of this concept. One thing that's always a problem, as you saw in previous slides, that there's always a sort of a mismatch between ReXFF time and temperature and experimental time and temperature. So we were kind of looking for a system where we thought we might go to a sort of a one-to-one correlation between ReXFF and maybe experiment, or actually look at connections between ReXFF and computational fluid dynamics. So I worked together with Yuan Xuan. He is a colleague of mine at Penn State, to see if we could make these type of connections between atomistic scale simulation and CFD, and in the end, experiment. So this was published, in 2017. So here you see the various people involved. So Chowdhury Ashraf he's now actually, his long sorry, this slide was not completely updated. He got his PhD about 5 or 6 years ago, Jaimeet Abhishek. And this was pretty much, this is Yuan, who has been collaborating with me on this particular project. And so what we essentially did was, we wanted to develop a concept of flame propagation in ReXFF. And how we did that was we took the sort of the following somewhat of a toy system, but still some relevance we thought here. We take a sort of a long rectangular MD box, and then this is arguably the pressure is significantly higher than it is in experiments. But what we can then do is we can break up one of the oxygen molecules on the left side, break it up into oxygen radicals. And then that will clearly initiate a reaction front that will then propagate throughout the box. And remember that this is a fully periodic system. So if my reaction propagates on the left, it will propagate from the left to the center, but at the same time, it will propagate from the right to the center. And then based on some observables, we can couple this to a speed and hopefully find some connection points with CFD or experiments. So this is how we did this. We introduced oxygen atoms on the left and the right. We have to do this at relatively high density just to make sure that we can capture the event under our accessible timescale. And then eventually we'll see a propagation. And we decided to find the propagation, you define the propagation by OH radicals. These are pretty easy to monitor in our simulation, so we can just see where they are and how they propagate from the left to the right, or for the left and the right to the center. So just some details of how we do this type of thing. So this was a microcanonical NV simulation, so there's no biases from thermostats involved. And clearly temperature, while the initial temperature is 1800 Kelvin, temperature will go up quite significantly during this simulation. And we had to start it at 1800 Kelvin because we wanted to make sure that the entire system was pretty close towards its auto-ignition temperature, but still a bit below. Yeah, at 1800 Kelvin, on the picosecond scale, this system is not going to react by itself, but if it gets a little bit of temperature impulse, it will get going. And then a continuum with kind of a similar simulation, where we pretty much have a distance along the z direction, a bit longer than in our MD simulation, but we can essentially compare these type of things. And these are the details of the CFD simulation that we used. And so this is what we kind of get. Yeah. So this is from ReXFF, and what the orange dots are pretty much the hydroxyl groups as we observe them during the simulation. And you can indeed see there's a real sort of propagation from the edge to the center. And so based on that, we can this is clearly requires a little bit of a judgment call, but we can figure out where pretty much the edge of my propagation front is. And then we can draw that as a function of time. And you can see indeed if we can draw some lines here, and that then indicates a sort of a propagation going on. And similarly, we can do that with the CFD simulation. We can see how the reaction front progresses as a function of time. And so based on that, we can also see how we can make sure this is reproducible. So we did each of the simulations 4 times, and we see indeed that this simulation was pretty reproducible. All 4 runs give fairly similar OH radical numbers. And out of all of this, we can actually get an ignition front speed. Now, this is clearly not ignition. This is OH radical, so there's clearly, but at least from a chemistry perspective, we can come up with a speed. And we found that ReXFF predicts 125 meters per second, continuum is 72. We were very happy with that because clearly there's a lot of jumps in theory that go on there. So we thought that quantitatively, this was a pretty good result. Now, what makes it more interesting is if you do it in a more qualitative way. So now the previous simulations are all done with butane. And so if you now change species, so we go from butane to toluene or to acetylene, we can essentially figure out which species has the highest flame speed or ignition front speed, to be precise. And we see that acetylene is much faster than butane, which is by itself much faster than toluene. Clearly, that makes sense. This is indeed the order of chemistry of these type of things, but these are then indeed numbers that these are more qualitative that you can start compare more directly with experiment. And if you look across the board, so here we see the comparison between normal butane, toluene, and acetylene. And clearly, at least the trend towards acetylene is very well reproduced between ReXFF and continuum. For toluene, there's a kind of a little bit of a mismatch, but you see indeed the order of the front speed is in reasonably good agreement. So we're pretty happy. There were significant method differences here, clearly. The trends are well reproduced. And given that the mismatch between basically the way that the mathematical framework between continuum simulation and ReXFF, we thought this was actually pretty good. Okay, so based on that, we haven't done these things, but we can indeed, this is something that could lead eventually to a simulation environment for steady flames. You have to significantly increase the simulation size for that, but this seems to be a possibility. And also what's later on, many acceleration tools have become available within ReXFF, like bond boost and hyperdynamics methods, and that might allow us to, as it's in time scale, get closer to CFD in experiments. So if you embrace these type of acceleration tools, you can actually get these type of comparisons, make it more easy to make those comparisons. Also in ReXFF, go to lower pressure situations that may help the comparison with experiments. All right, so as the next stage, Chowdhury actually started looking more details at that 2008 force field. And we found there were various issues with it that we thought this was a good moment to see if we could rectify them. One of them, the 2008 force field is absolutely awful for the graphites for the graphite and graphene mechanical properties. It was never trained for it. It described it okay as a chemical compound as far as chemical stability is concerned, but it just had no, it gave an awful elastic modulus. Elastic modulus was probably about 10 or 20 times too large. Another thing that didn't work that well with that force field was the description of carbon monoxide. Carbon monoxide is clearly a pretty weird chemical species in all ways and forms. And so we wanted to apply this force field to syngas, and it turned out there were some issues with some of the key barriers there. Another thing that we noticed was that O2 was actually significantly too reactive, because this particular transition state for hydrogen transfer between hydrocarbons and O2 was essentially significantly too low. So that means that the force field predicted the hydrocarbon reactivity was higher than it should be. So we essentially then we developed that force field. One thing that we wanted to include was the carbon condensed phase, which we already had done before in 2015. So we just blended these parameters in. And then overall, we wanted to expand the training set, add more species to it, and particularly indeed carbon monoxide reactions and these hydrogen transfer reactions. So that worked out pretty well. So this is the issue that I was talking about. So you look here in green. This was the 2008 reaction for carbon monoxide with hydrogen. Very high barrier in 2008. So even if you were to mix hydrogen radicals with carbon monoxide, essentially it would be almost non-reactive at low temperatures. While in 2008 the 2016 force field is much closer to the DFT numbers, just a slight barrier, nothing too bad. Also, the description of the HCO radical, which is quite central to any of these type of chemistry, was completely incorrect in the 2008 description. It essentially was a linear radical, but it should be an angular radical. So we managed to correct that. We had to do that. We had to change some of the functional form a little bit. This is now indeed, this is something that we ported to LAMMPS and to ADF. So in LAMMPS you can simulate this, but you need to run it with a particular patch which we have available. And here's just some sort of highlights from the training set. Looks very similar to the Chenoweth force field that I described, but some new elements that were in there were equations of state for graphene and diamond. And then we greatly expanded some of the reaction entities, especially the carbon monoxide related reaction, but also many reactions with HO2 and peroxide. And overall, we got a quite good agreement for this force field between those data. Here are some particular reactions related to carbon monoxide reaction, where we look at HCO species. And overall, across the board, we see that the 2016 force field follows the DFT data quite well. DFT data in dark blue. And so the 2016 force field here in red. So that was fine. Now we and also, oh yeah, this issue resolved. So we didn't realize this until we were made attentive of this. But while formerly the 2008 force field was trained for this reaction, it turns out there was a particular reaction path that we hadn't considered there that actually led to much lower transition state for this reaction. Actually, the transition state is not even a transition state; it's actually more of an intermediate, because it's more stable than the separated CH3HO2 species. And so that was essentially fixed in the 2016 description. Okay, so now I want to check out if it works. So we applied it to a couple of applications. Let's show you some highlights for this. So we essentially tried it for the carbon monoxide system, which was our main target to start with. So we build these systems up. We always have the energy minimized, and we equilibrate it at low temperature. We use a temperature ramp, slow temperature ramp to take it to the target temperatures. And then we do a prediction run. This one is at 3000 Kelvin. We can also run it significantly lower temperatures, but this is just, and so this is a pretty nice and small scale. So this entire procedure that you do here takes about 1 day on a single CPU. So that's quite manageable. And so with that, we can essentially look through the chemistry. We see when the reaction begins to initiate. If you see here in red is pretty much our temperature ramp. And you can see how the various species respond. We see indeed that the initiation reaction for the 2016 force field is significantly different than for the 2008 force field. The initiation reaction of 2008 force field are at a relatively low temperature, but they actually move to slightly higher temperature in the 2016 force field. And we also see a much richer chemistry. So in the 2008 force field, all we saw is what is on the top left. This was all that got populated, because all the routes that led through the HCO radical were essentially blocked, because that radical had such a high barrier formation. So in 2016 force field, we actually see indeed the pathway towards HCO formation. So we can indeed have a much more complex chemistry going from carbon monoxide to carbon dioxide. And we can kind of figure out which species we observed. So in 2008 force fields, many species that are observed in literature are pretty much absent from our simulation. Once again, because the HCO path is pretty much blocked. In our 2016 force field, we see all these reactions aspects for a couple of ones that are actually relatively rare in literature. And the reason why we didn't see them is simply because our simulation box was pretty small. So if you were to increase the size of the box, we'll probably observe some of these rare events as well. All right, so looking at the CH4 system, so we see that the 2016 force field is significantly less reactive towards CH4. Sorry, I saw a question coming. Okay, I'll get to your question in a second. Sorry. The 2016 force field is significantly slower in these reactions and much more accurate as far as comparison with experiment is concerned. So we get essentially in the 2008 force field, we get this early formaldehyde peak, which essentially is completely absent in the 2016 force field. So there's essentially a first state ignition that we feel is essentially incorrect. That essentially is almost skipped over in the 2006, or if it happens, it's a much smaller level, and it happens at much later in the simulation. All right, so that was in 2016. Since then, we've been applying this 2016 force field to a wide range of systems, some new systems that we actually hadn't even considered during development. So Aditya Lele has been using this for essentially expanding on the JP10 work, looking at other type of bicyclic, tricyclic potential candidates as replacement fuels and looking at their reaction chemistry, finding indeed that it agreed quite well overall. These were all structures that were nowhere near the training set, but we all found pretty good agreement with DFT. We used it for Stroot growth using different precursors, using, for example, benzene or phenoxy precursor, and found indeed that these precursors have very different initial Stroot conversion pathways. The benzyl radical leads to a much larger amount of 6-membered ring formation. And then new areas it opened up for us. We expanded that in 2019 to nitrogen. And then we essentially apply these force fields to essentially carbon fiber formation, where we heat up these precursors with and without oxygen in other different environments. And we can essentially look at their graphitization. Remember, this force field is quite accurate for graphite, mechanical and chemically. And we can indeed see these type of larger clusters getting formed. So we can directly connect initial structures to carbon fiber structure. And we can also get all sort of nice detailed chemistry. This paper here from 2020 shows, for example, how the nitrogen doping can affect the graphitization chemistry. Now, we also can manage to expand this with transition metals. So in 2020, we expanded this force field to copper, where we started looking at these pretty fascinating copper nanoclusters that essentially are, this is getting towards sort of flame synthesis type application, where we put in a hydrocarbon area or oxygen, and we see how these nanoclusters essentially have very complex morphology changes upon exposure to hydrocarbons. And some unexpected applications where it actually worked quite well for. It is more of this is an interface of a copper sheet with various sort of little extrusions in there, and we drape graphene over that. And the experiment, they see all sort of relatively complex deformation pathways for graphene, and indeed these were very well reproduced with ReaxWeb. So this is kind of a cute simulation. You just drape the graphene over this copper extrusion, and see on one side it collapses back on the surface, on the other side it causes keep dangling over. So we can measure these type of draping angles. And it turns out that whatever we predicted with ReaxWeb compared quite well with experimental observations. Now, sort of new areas that we're moving into are essentially things like material synthesis. This was also work from Aditya Lele's PhD work, where we extended the combustion force field to boron nitride using these B2H6 and NH3 precursors. And this was once again a sort of a cyclic process. We had a series of core reactions that we trained the force field for. Then we used the force field to generate new structures, have a sort of a cycle going on. We took BVLRP as our favorite simulation tool. And we trained this. So initially, the force field wasn't looking too great for some of these structures, but after training, we got them all reasonably well aligned. And then we can look at precursor effect on material synthesis. So we can look at HP and H precursors and BM precursors. You see that the HP and H precursors produce very different structures. This is all gas phase stuff still, where we, for example, see hydrogenated edges and kind of pretty well-defined flat two-dimensional hexagon structures. BM precursors lead to much faster growth, but also the structures that we get are much higher curved. So these are still all many hexagon type sort of rings, but they are much more complex sort of nanotube or curved nanotube shapes. And so with that, we can come up, for example, design these type of quality factors, where we say that hexagons 3, 4, and 6 are all high quality, while hexagon 4, since it's only borders on one other hexagon, it's a low quality hexagon. And based on that, we can design quality factors and relatively quickly link, as for example, synthesis temperature to quality. And that clearly depends what you want to achieve. Sometimes, indeed, this product down here may be more desirable than the closed structure. Now, recently, also, well, later on, we used this force field to expand it also back to surface chemistry. This was a collaboration with Ben Louis from Kansas State University, where I expanded this force field to a nickel chromium alloy. And we can essentially simulate then the deposition of these boron nitride species on the surface and look directly at their growth. And this gets you to a time scale that is pretty directly comparable to experiments. Of course, indeed, if you use modern microscopy techniques, this is pretty much an observable quantity. And you can clearly follow all sort of nice details of the growth as a function of time and get and explore what essentially drives the synthesis. All right, that brings me to the end of my presentation. Just some highlights. So I talked a bit about our pathway towards the 2016 hydrocarbon combustion force field, how we took the 2008 force field and upgraded it with C1 chemistry and graphite chemistry, and how that opened up all sort of rigid channels for us, not directly between necessarily what we would call hardcore combustion, but the concept of combustion really transfer well to many sort of neighboring areas. So we used it for carbon fiber, but also particularly in my group, we're very interested in exploration of connections between combustion chemistry and material synthesis. So things like flame synthesis, where you have indeed combination of a metal precursor and a combustion environment. These are very nice areas to use these methods in. All right, thank you very much for your attention. I'll be very happy to take questions.